So advantage of using this capacitor, the capacitor provide a burst of the charge. The total charges which are supplied by the battery to the capacitor will be same as total charges which the capacitor will supply to the component. But a battery, if you sketch a graph for a battery, it was supplying you a constant charges. But what capacitor will do, in the beginning, maximum amount of charges will flow out. So maximum current is there. And with the passage of a time, the charges will decrease. And it's an exponential change, a drastic change. Due to this drastic change, like in the beginning, it's a maximum amount of charges will flow out. So it will provide a greater current, means a greater magnetic effect of the current. So using this magnetic effect, if for example, if any device or if any mechanical device which use magnetic effect of the current, example a fan. So initially, because the fan is stationary, so it is because of its inertia, it will be difficult to move. But once it is moving, it is easy to continue its movement. So the moment when you switch on the fan, actually it happen in a short time. Your capacitor charge and discharge. The moment your capacitor discharge, it provide a jerk to the, or provide greater burst of the charges to the fan, or greater force, so that a fan can move easily. Is it clear? And another example, another use of the capacitor, you can find a light which is used inside the car. When you open the car doors, the light will be switched on. Once you close this, instantly the light does not switch off. It takes small time to switch off. Reason for that, because there's a capacitor also used there. So moment you close the doors, so capacitor discharge, as a capacitor is discharging, the light will remain on for some time. Later in this topic, I will discuss the applications of the capacitor. There are many circuits which use these capacitors. So right now it's about charging and the discharging of a capacitor. And the discharging and the charging also depends on another factor, which is called the external resistance. So if we have a higher value of external resistance, the capacitor will take more time to discharge. If a smaller value of external resistance, the capacitor will discharge in a short time. These are the graphs, the charging graphs for the capacitor. So when you're charging a capacitor, if you sketch a graph, why the value of the current is maximum and then the value of the current is decreasing? Because initially, like these are the two plates. These are the two plates of the capacitor. So example, the positive and the negative terminal. What happened in the beginning, because there are no extra charges on these plates. So no extra charges on the plate. So electrons which are coming out from the battery, they will move faster in the beginning. As a movement of the charge or electron is called current. That's why the current started with a maximum value. But when this electron reach here and the second electron is coming in this wire, there is a repulsion between the electron which is present on the plate compared to the electron which is coming from the negative terminal of the battery, or moving from the negative terminal of the battery. So what happened? The light charges repel each other. So compared to the first electron, this electron will slow down. And then another electron will come, because already there are two electrons. So this electron will further slow down. So as the movement of electron decreases, as we know, the current is charge divided by time. The electrons are taking more time to flow. So if they're taking more time to flow, the current will decrease. And eventually, we have enough electrons on this plate so that no more electron can move. That's why the current is zero. Is it clear, the explanation of charging current for a capacitor? Because the definition of the current is a movement of the charges, or the flow of the charge is known as electrical current. Then if we, for a potential difference in time or voltage in time, in the beginning smaller voltage, but as with the passage of time voltage increase, rate is decreasing but voltage increase, and eventually it will be constant. What is the reason for that? Because as there is no repulsion, between the first electron is there. If when it moves, it does not experience any repulsion, so less or no work, small amount of work done. That's why the voltage is initially it is zero. Then when one charge will move, work done increases. As there are more charges, so you need more energy to push the charge on the plate. That is why the work done is increasing. And eventually, when you are not able to move the electrons, it means that the voltage which you are supplying balances with the voltage of the, or energy which you require to move the electron from battery to the plate is same. That's why there is no net movement of the charges. That's why the voltage is constant. So in the beginning, why the voltage is zero? Because there is no repulsion. But with the passage of a time, voltage increases, and eventually the voltage is constant. Once the voltage constant, it shows that the voltage of a supply is same as the voltage of the battery. Otherwise, if the battery voltage was lower than the capacitor voltage, then there will be a reverse movement, means the charges will flow from capacitor to the battery. But in this case, so initially we have to do a smaller amount of work done to push the charge, but as the number of the charges on the plate increases, so we have to increase the work done, or we have to do more work done, and in the end the work done will be zero. Means in the end the work done, once the battery voltage is same as the voltage of the capacitor, there is no charge stored or no extra work done, or work done will be constant, or potential will be constant. So if you have a 6-volt supply, once this plate will reach 6 volt, the potential difference or voltage is 6 volt, then the capacitor will stop charging, it will not charge. But before this voltage, the capacitor will charge. And charge on the capacitor, as you can see, in the beginning there is no charge on the capacitor, but with the passage of the time, the charge increases. Like there are more charges or more electrons will be there on the capacitor. So charge will increase, voltage will increase, but the current will decrease. This is for charging. What about discharging? For discharging also it's the same. The current is the same. Why the discharging and the charging currents are same? The reason is that because current is a flow of the charges. Current is not something which is stored. It's just a movement or the flow of the charges. So when you have a parallel plate capacitor, you connect a battery, and not battery because it's a discharging. So you connect a bulb or a lamp which can use these energy stored in the capacitor. So as we know, when the capacitor is charged, so this will have majority electrons and this will have majority positive charges. You should make equal number of positive and negative charges because the net charge is zero on the capacitor. It only stores electrical energy. Like charges repel each other, so there are more electrons in the beginning, so more repulsion into the conventional current from positive to negative, but I'm explaining in terms of movement of electron. So in the beginning, more greater repulsion, so electron will move fast. But as the number of electron on the plate decreases, the repulsion decreases, so then electron will slow down. And eventually there is no movement of electron. It shows that there is no current. That's why the current started with a maximum value and it decreases. Eventually the current is 0. Is it clear? Same way, the potential or the voltage across the capacitor will also decrease. Like your parallel plate capacitor was having a voltage of 6 volts, and you connect a lamp, or say you connect a resistor and a lamp. Because capacitor store and transfer its energy to the component. So this is a resistor. So in the beginning, the moment you connect, the capacitor voltage was 6. But what happened? As the capacitor is transferring the energy or doing work done per unit charge, so voltage of the capacitor decreased. The total will remain 6, like, but the voltage of the capacitor, like example, it is 0. So voltage of the capacitor, in the beginning it's 6, but what happened, like example, it becomes 5. So if voltage of capacitor becomes 5, maybe 0.25 volts is across the lamp, and maybe 0.75 volt is across the resistor. Then what happened? It become 4. So if it become 4, the voltage here will also increase. The voltage across the resistor will also increase. Originally it was 6. So when it becomes 4, so both voltages will increase and the voltage of the capacitor will decrease, and eventually the capacitor voltage will be 0, that it does not have any work or cannot do any work done per unit charge. And the charge on the capacitor, as in the beginning, maximum charges are there, and with the passage of a time, the charges start to decrease. So the formula which we can use to find the current at any instant of the time, or charge or voltage for a capacitor, because it's an exponential change. So the equation which gives this formula, which shows this equation graph line. So the formula is I is equals to I naught e raised to power minus t over RC. What is I naught? I naught is the maximum current. That's I naught. What is I? I means current at a specific time interval. Like example, if in a question they ask what is the current after 2 seconds, after 3 seconds, 4 seconds. So the current at a specific time interval, that is known as I. What is R and what is C? R is the resistance, because the current which is passing through the capacitor, or the flow of the current through the from the capacitor, depends on the external resistance or the value of the R. So this R is a circuit resistance and C is a capacitance, like how much voltage a capacitor can store per unit charge. Same way, the formula which relate voltage and voltage, if we need a voltage of a capacitor after a certain time interval, so it's a similar formula. It's V is equals to V naught e raised to power minus t over RC. What is V naught? V naught is the maximum voltage. V is the voltage at certain time interval. R is the external resistance through which the capacitor discharge here, because it's a discharging graph, and C is the capacitance of a capacitor. And in terms of charge, the formula Q is equals to Q naught e raised to power minus t over RC. So Q naught is a maximum charge. Q is the charge at a particular time interval. R is the external resistance, C is a capacitance, and T is the time at which we are finding a charge. So these equations you have to learn. This is for discharging. Actually, the charging equations are also correct, but only the difference is about the V naught and Q naught. This is the same equation because the graph is same. So I is equals to I naught e raised to power minus T over RC. What about this? V is equals to V naught minus e raised to power minus T over RC. So what is V naught? V naught is a maximum value now. In the discharging, it's a starting value. In the charging, it's a maximum voltage. V is the voltage at a certain time interval, and T is the time. R is the capacitance. R is the resistance through which the capacitor is charging. But this time, this R is a charging resistor, like resistor in the path of the charging. And in the previous example, the R was the external resistance, means a resistor through which the capacitor was discharging. And same thing, Q is equals to Q naught e raised to power minus T over RC. And what is the meaning of RC? RC is also having a meaning. When R multiplied by C, actually R multiplied by C will get the time. How we get a time when R multiplied by C? R is the resistance. What is the resistance? Is voltage divided by current. And what is capacitance? Capacitance is charge per unit voltage. So charge divided by voltage. So this V will cancel with V. So what I can say Q is equals to I. Q divided by I. And what is, if you remember the formula for current, current is charge divided by time. So charge is equals to current multiplied by time. So in place of charge, if I write current into time, so current will cancel with current, and what you're left with? You're left with time. So what is this time? What is the significance of this time? This is called a time constant. But what is the meaning of this time constant? This time constant means when the capacitor reach 37% of its original value, because how we know or how we suggest like this is a time constant or this T is a time constant, you can use this equation. You have formula V is equals to V naught e raised to power minus T over RC. If time is equals to same as the product of RC, so we can say V is equals to V naught e raised to power minus, in place of T I'll write RC. V is equals to V naught e raised to power minus 1. What is the answer for e raised to power minus 1? Press shift, e raised to power minus 1. What's the answer? E raised to power minus 1. You will find this E in on press shift, then instead of ln press this E. Yeah, what's the answer? E raised to power minus 1.
0.367.
Yeah. So V is equals to V naught. It's equals to 0.367.
368.
368. Or if I say it can be 368, or I can say 0.37. Okay. And if I write this decimal in terms of percentage, I can write this as 37 divided by 100. 0.37 I can write 37 divided by 100. If something is out of 100, we can say 37. I can also say 37%. So what does it means? V naught is equals to 37%. So what it shows? It shows that when the value of the RC shows that when is the voltage become 37% of the original or the maximum voltage. Like if the maximum voltage was, say the maximum voltage was 100. So 37% of 100, it will be 37. So how much time the capacitor will take to discharge to 37% of its original value. For a simplification, I took starting value as 100, but starting value can be any number. But how much time the capacitor will take so that its voltage will decrease from a maximum value, its voltage decrease 37% of the maximum value. That time interval is known as the RC. So whenever resistance of a capacitor multiplied by capacitance, you will get the value, and that value shows how much time the capacitor will take to discharge 37% of its original value. Is it clear? So if original value is 100, so how much time it will take? 37% of original value means 37. If original value is, for example, 1000, so then how much time it will take? 37%, it means 370. So multiplying R with C, you will get the value of the time, and this time is the time taken by capacitor to discharge 37% of its original value. So using the RC, we can just, this is just a benchmark, you can say, to identify that how much charge was left or what is the voltage left on the capacitor after time constant. And normally the complete discharging time for capacitor is approximately, this is not exact number, but it is approximately 5 times RC. Capacitor will discharge completely approximately 5 times the value of the RC. Like example, when you multiply R and C, say you was getting answer 2 seconds. If a question is how much time a capacitor will take to discharge completely, so to discharge completely, the time is approximately 5 times RC. So value of RC is equals to 2. So 5 multiplied by 2. So it will take 10 seconds to discharge completely. It means the value will be 0, approximately 5 times the RC. It's an exponential change. It's not a linear or a proportional change or inversely proportional. That's why if first 37% it was discharging and taking 2 seconds, but for remaining 30 seconds, remaining voltage to decrease to 0 value, it will not take the same time because it's an exponential change. So these are the formulas just now I discussed with you. Equation for discharging: Q is equals to Q naught e raised to power minus T over RC, V is equals to V naught. So I want you to just copy these equations. Equation for discharging. Okay, now this is this is a graph for voltage and charge. Voltage is in volt, but the charge is microcoulomb. You can see they are directly proportional. Voltage is double, charge is double on the capacitor. Voltage compared to the first value, it's 3 times. The charge is also 3 times. Voltage is 4 times, the charge is 4 times. Voltage is 5 times, the charge is also 5. So when you sketch this graph, you'll get a straight line. And when you get a straight line, so when you get a straight line, it means they're directly proportional or the ratio is constant. As the ratio is constant, this constant ratio is known as capacitance. Now, the capacitance of a capacitor, like how much charge can be stored per unit volts, depending on two factors, mainly three factors, but two are the main factors. It depends on the surface area. Like if you have large plate surface area capacitor, it can store greater amount of charge as because more area means more charges are exposed. That's why it can store greater amount of charges on the surface. So larger surface area will store more charges. And it also depends on distance between the plates. If the two plates of the capacitor are very close to each other, then it can store greater amount of charge as compared to the two plates which are far away from each other. Reason for that, because when the plates are closer to each other, they have a strong electric field between them. So when they have a strong electric field between them, so the electron which will come on one plate, they can push the other electrons or electrons from the other plate so that greater amount of positive charge can be induced or remain on this capacitor. So the capacitance directly proportional to area. Large area capacitor can store greater amount of charge, so higher capacitance, and it is inversely proportional to distance between them. So when I combine these two factors, I will say it will be A divided by D. So it shows that capacitance is directly proportional to area, and it shows it is inversely proportional to distance between the plates. Copy this one. Then the capacitance, the how much charge stored or because instead of charge, it is storing electrical energy. So it also depends on the presence of any dielectric material. If you put any material between the plates of the capacitor, the charge stored will be higher. Why the charge stored will be higher? Because look, if there's nothing between the plates, like in nothing in that sense, like air is there, but one is positive, say maybe three positive charges, three negative. But if you put a dielectric or any material between or make, so what it caused a separation of the charge within the material. So then plus minus, minus plus and minus plus. So you can see greater number of charges are induced within the capacitor. So it increases the capacitance. So by placing any dielectric here refers to a material which is having charges known as a dielectric material. So if you place any dielectric material between the two parallel plates parallel plate capacitor, then its capacitance will increase. It can store greater amount of charge per unit volts. Now, for capacitors in parallel, so if two or more capacitors are in parallel, as we know, the parallel circuits, the voltage is same. So they all receive the same volts. If the capacitance of first capacitor is C1 and the charge is Q1, second one is C2 and the charge is Q2. And the total charge which stored is Q. So I can say the total charge Q is equals to Q1, the charge on capacitor 1 plus the charge on capacitor 2. And as we know, Q is equals to CV. So C multiplied by V. So in place of, I can write the total multiplied by total voltage, first capacitance multiplied by voltage, and second capacitance multiplied by voltage. Why I took the same voltage for all? Because they are in parallel, so they will receive the same voltage. So V is common, V will cancel out. So if two or more capacitors are in parallel and we need a combined capacitance, we will simply add them. This is the formula to get the capacitors in parallel. But if they are in series, as you can see, they are in series. So what happened? If this is store 5 charge plus 5, this will be minus 5, then other will also be plus 5, minus 5. So means the charge stored in series will be same. The total charge in each capacitor will be same. If this store 10 coulomb total, this will be 10 coulombs. But what happened? The voltage will divide. So V is equals to V1 plus V2. And Q is equals to CV. So V is equals to Q divided by C. So we can divide. The charge will be same. The total charge is same as the charge on each capacitor. So this all Q will cancel out and the combined will be reciprocal. So it's easy to remember for parallel plate. As you remember, for resistors, when resistors were in parallel, we were adding a reciprocal. But when capacitors are in parallel, we are directly adding the capacitance of individual to get the combined capacitance. And in case of resistor, when resistors are in series, we calculate the combined resistance by adding them. But in case of capacitance, we take a reciprocal, or it will be 1 over Ct is equals to 1 over C1 plus 1 over C2. Is it clear? The concept? So you have to keep these formulas in mind to solve a question. So this is a worked example. Two capacitors, one is 5 microfarad, another one is 2 microfarad, are connected in parallel to a DC supply. So you can see 50 volts applied to the combination. We apply 50 volts. The total charge on each capacitor. How to find a charge on each capacitor? We have the formula Q is equals to CV. So capacitance is given for each capacitor and voltage is also given. So if I need a charge for 5 volt, if I need a charge for 5 microfarad capacitor, so 5 multiplied by 50. If I need a charge for 2 microfarad capacitor, so it's 2 micro means 10 power minus 6. That's why this is 10 power minus 6 multiplied by 50. You will get 100 micro coulomb. That's a total, that's a charge. Then they're asking the total charge. So what is the total charge? The total charge is a sum of charge present in each capacitor. We add them, so we'll get 350. Then we need a combined capacitance. So how to find a combined capacitance? So Ct is equals to C1 plus C2. When capacitors are in parallel, we'll simply add. So 2 plus 5 or 5 plus 2, it will be 7 microfarad. Then the total charge stored on the combination. So the total charge stored on the edge, it's obvious because the total charge of the individual charge was like 250 and 100. So total charge of the combination should also be same, but you can work out with the formula as well. You have the capacitance, which is 7 microfarad, and you have the voltage 50. When you multiply, you will get the same answer. So why the answer of 2 and 4 are same? Because the individual charge, the sum of individual charge is equals to total charge stored on the capacitor. Is this clear, the word example? But if two or more capacitors are in series, so what we will do, like example, a 16 microfarad and 48 microfarad, they're connected in series to a 40 volt supply. So total voltage, we need a total capacitance because they are in series. So reciprocal we will add. So this is plus 1 over Ct is equals to 1 over C1 plus 1 over C2. then we take a reciprocal and find it will give us 12 microfarad. 12 microfarad is the total capacitance. Then the total charge, how to get the total charge? So we have the total voltage, which is 40, and combined capacitance is 12. So Q is equals to CV. When we multiply, the total is 480 micro coulomb is there. Charge on each capacitor. So how to find the charge on each capacitor? The charge on each capacitor is same as the total charge on the capacitor, like the combined capacitance. So in series, when capacitors are connected, both capacitors will have the same charge. So if the total charge is 480 microcoulomb, the charge on capacitor 1 will be 480 and capacitor 2 is also. So charge on each capacitor in series must be same. That's why it is 480 microcoulomb. And then if we need a potential or a voltage across each, so how we can find a potential or voltage across each? So we have the formula Q is equals to CV. So we have the charge on each. The total charge is same as the charge on each. And we have the capacitance. So we can find the voltage of individual capacitors. Is it clear, this example? So capacitors can be placed in series. So when they are in series, the total charge is same as the charge on each capacitor.